Sure. Skip this ad, just like you skipped that on bio.
Professor Ebenso, is there any problem to reach our conference, our 16th conference on ICMES 2020?
راك يكتب لي في الفيسبوك الحاج.
Hammoudi, what's going on?
Yes, 1 minute to let time to Professor Ebenso to connect his computer. Yeah. Professor Ebenso, can you activate your micro, please?
Hammoudi, send a note to Ebenso to show up his camera and his microphone.
Yes, he listen us.
No, he don't listen. He don't listen because his camera is closed.
But he listen us. He is live with us, but his camera and micro are not activated. Please, can you activate your micro first and your camera, please?
But you have to send him a message. Send him a message, but otherwise he will not know this. He leave now. He leave. Il a quitté.
Oui. Okay, to surpass this problem, I go ahead. I am pleased to receive you on this virtual conference on the 16th conference. Receive you on this virtual conference. Professor Savas Kaya from Sivas, comme Hurriyat University, Sivas city from Turkey, will present his talk about the metal chelation effect on the chemical reactivity on diazenyl ligand to composant theoretical and computational investigation. You have about 30 and 35 minutes to talk. Now I see Ebenso participates, but I give you ahead after the conference of Professor Kaya. Welcome. You can begin your talk. Thank you so much.
Thanks a lot, Professor Hammoudi. Firstly, thanks a lot to all organizers of the conference. I am very happy to be here. My presentation is about the metal chelation effect on the chemical reactivity of diazenyl ligand, theoretical and computational investigation. Firstly, I want to start with the conceptual density functional theory. Conceptual density functional theory is known as DFT of chemical reactivity. In this theory, chemical reactivity parameters such as chemical potential, electronegativity, chemical hardness, and shortness are defined as derivatives with respect to charge of total electronic energy. You can see here that chemical potential is the first derivative with respect to number of electrons of total electronic energy. On the other hand, chemical hardness is a second derivative with respect to number of electrons of total electronic energy. Lastly, we can say that Pearson introduced the chemical hardness concept, proposed that softness is the multiplicative inverse of the hardness. Using finite difference method, Pearson and Parr proposed the following equations to calculate the electronegativity and chemical potential and hardness values of chemical spaces. I want to talk about firstly about this difference between absolute electronegativity and Mulliken electronegativity definition. Here, to calculate the electronegativity and chemical hardness, ground state ionization energy and electron affinity values are considered. On the other hand, in the definition of Mulliken, valence state ionization energy and electron affinity values are considered. It is well known that valence state values are obtained in the light of spectroscopic data. In this stage, I will introduce my new equations proposed to calculate chemical hardness and electronegativity of molecules. Let me start with the definition of chemical hardness. Chemical hardness is defined as resistance towards electron cloud polarization or deformation of chemical spaces. In the literature, there are three electronic structure principles about this concept. One of them, hardness equalization principle. Second one, hard and soft acids and bases principle. The last one is maximum hardness principle. In the derivation of new molecular hardness equation, we considered, myself and Professor Jamakaya considered hardness equalization principle. For that reason, I will explain the meanings of hardness equalization principle here. Sanderson proposed electronegativity equalization principle considering the relation between electronegativity and charge. It is important to note that all such equalization process about chemical reactivity descriptors are explained by means of the correlation between the mentioned reactivity descriptor and charge. In the old past, Professor Dipankar Datta, who is my collaborator, proposed that hardness of all atoms in a molecule during molecule formation is equalized like their electronegativities. A second electronic structure principle proposed for hardness concept, a hard and soft acid-base principle of Professor Pearson. This principle states that hard acids prefer to coordinate to hard bases and soft acids prefer to coordinate to soft bases. And last electronic structure principle proposed about chemical hardness concept is maximum hardness principle. Shortly, I can tell you maximum hardness principle present the relation between chemical hardness and stability. And it is among the most widely accepted electronic structure principle of chemical reactivity. The maximum hardness principle introduced by Pearson explains that at a given temperature, a chemical system tends to arrange itself so as to achieve maximum hardness, and chemical hardness can be considered as a measure of stability. Later, Kattarash, considering the inverse relation between hardness and polarizability, proposed the minimum polarizability principle, states that natural evolution of any system is toward a state of minimum polarizability. There is an electronic structure principle more in the literature. It is minimum electrophilicity principle. Minimum electrophilicity principle states that the natural direction of a chemical reaction is toward a state of minimum electrophilicity. From here, it can be seen that the molecules with low electrophilicity value are more stable compared to others. I want to talk about an error in the literature here. Here I presented new definition of the hardness, and below I presented old definition of the chemical hardness parameters. You can see that there is a difference between them. In old definition of the hardness, 1/2 coefficient is used in the equation. On the other hand, there is no any coefficient in the equation. The equation given above new definition of the hardness and the equation given below old definition of the hardness. There is a misunderstanding in the literature, especially in corrosion studies. If we use new definition of the hardness, we can use the par electrophilicity index without any change. But if we use old definition of the hardness in the analysis of the chemical reactivity of molecules, in the using of old definition, we should use here 4 coefficient. In this way, we can obtain compatible results with Pearson's hard and soft acid-base principle. And here I want to talk about second electrophilicity index. Many authors in the papers use par electrophilicity index, but much of the authors don't know second electrophilicity index proposed by Zempali, who my collaborator from Germany. In this second electrophilicity index, it is based on ground state ionization energy, ground state electron affinity, and chemical hardness values of chemical spaces. And I can tell you, second electrophilicity index provide more good results compared to that of par electrophilicity index. For that reason, in the computational studies, I propose, in addition to first electrophilicity index proposed by Pi, I propose the using of second electrophilicity index also. We presented any molecular hardness equation. In the beginning of the study, we proposed a new atomic hardness scale. Atomic hardness scale mentioned is given by equation 6. Here, E and P parameters are based on ground state ionization energy and electron affinity of atoms. Sigma represents the charge of atom. The equations for A and B parameters given below, based on ground state ionization energy and electron affinity values of atoms. After that, we applied our atomic hardness scale to 4 a molecule having n atoms, we can write these equations for atom 1, these equations, for atom 2, these equations, until atom n. According to hardness equalization principle, we mentioned it before that, like electronegativity, hardness of all atoms in the molecule during molecule formation get equalized. And on the other hand is now that the sum of particle charge of atoms in a molecule is equal to charge of a molecule. For that reason, we can write equation 7 and equation 9. Combining all relation presented here, finally, we obtain the following molecular hardness equation published in Molecular Physics Journal by myself and my supervisor, Cemal Kaya. This equation is an important way to obtain a molecular property from atomic properties. It is important to note that in this equation, eta m and qm are chemical hardness of molecule and charge of molecule, respectively. N is the total number of atoms in the molecule. There is another molecular hardness prediction methodology in the literature. It is data geometric mean equation. According to data, molecular hardness can be calculated as the geometric mean of the atomic hardnesses. In this table, we compared our results with the results of data. You can see that all results are very compatible, but I can tell you Kaya molecular hardness equation has an important advantage compared to data equation. This advantage is that Kaya molecular hardness equation can be used for both ionic molecules and neutral molecules, but data equation is for only neutral molecules. Secondly, we presented any molecular electronegativity equation. As beginning, we used Kautsky and Margray electronegativity definition presented using equation presented here based on E, A and B parameters like atomic hardness scale. We presented the mathematical formulation of A and B parameters and said that they are depending on atomic ionization energy and electron affinity. Sigma is the charge of atom here. Again, for a molecule having n atoms, we can write these equations for atom 1, for atom 2, for atom 3, and for atom n. According to Sanderson's electronegativity equalization principle, we can write kappa 1 is equal to kappa 2, and we know that total charge of a molecule is equal to the sum of the particle charge of atoms in the molecule. Finally, we obtain these molecular electronegativity equations. Now I will mention from lattice energy. Lattice energy is a key parameter for the prediction of the stability of ionic compounds. Lattice energies of ionic crystals have a significant function in the analysis of the thermodynamics as well as prediction of stability of ionic crystals. It is important to note that lattice energy isn't a quantity that can be experimentally determined directly, because in the practice, the crystalline solid dissociates into atoms and not into gaseous ions. For that reason, lattice energy values calculated using Born-Haber-Fajans thermochemical cycle are known as experimental values. In the literature, there are three famous lattice energy equations. One of them Born-Lande equations, other Born-Mayer equations, and last one is Kapuscinski equations. The meanings of the parameters showing in these equations are given below as detailed. You can see here. Actually, we talked about maximum hardness principle and minimum polarizability principle. Shortly, maximum hardness principle states that hard molecules are more stable compared to soft ones. Minimum polarizability principle states that the natural evolution of any system is toward a state of minimum polarizability. In the light of maximum hardness and minimum polarizability principle, we think that lattice energies of inorganic ionic crystals can be calculated with the help of their chemical hardness and molar volume values, because both lattice energy and chemical hardness and polarizability can be considered as a measure of the stability. In the graphs, instead of polarizability parameter, we used, instead of polarizability parameters, yes, we used molar volume parameters, because these equations, known as Lorentz equations, shows that polarizability of a chemical space is proportional to its molar volume. You can see this ratio given here and experimental lattice energy values. There is a remarkable correlation between them. You will see in the future slide, this combined parameter is now Kaya combined parameters proposed for chemical reactivity analysis of molecules. In the last stage of the analysis made, we proposed the following equation for calculation of lattice energies of ionic crystals, and these equations published in a good journal, Inorganic Chemistry Journal of American Chemical Society. In this new equation, you represent the lattice energy of ionic crystals. On the other hand, we presented here the mathematical formulation of ionic strength. In this table, a comparison of lattice energies determined with some theoretical methodologies for alkali halides is presented. You can see from this table that Kaya lattice energy equation presented in the slide presented before provides compatible result with experimentally observed results. In a last study published by myself and Professor Laszlo von Szentpali, we analyzed the success of Kaya combined descriptor for the analysis of the solid state reactions. In this table, some solid state reactions occurring between alkali halides, enthalpy Gibbs free energy, first electrophilicity index, second electrophilicity index, molecular hardness, Kaya combined descriptor are presented in this table, and we realized that Kaya combined descriptors explain the exothermic nature of all reactions as a successful format. In the last stage of the presentation, as a reference molecule, we considered a phenol compound and its 4 metal complexes. Their optimized structures are given here. In this table, many quantum chemical parameters calculated for studied compound, and it is 4 metal complexes presented. It is clear from the data presented in this table, combined descriptor given here are very successful in the explanation in the prediction of the stabilities of the studied compounds. And according to Kaya combined descriptor, we can tell you between studied complexes, chrome, iron, nickel, and zinc complexes, iron complexes is more stable compared to other complexes because you can see that combined descriptor value for iron complexes presented here is larger than that of others. Evet, thanks a lot to all people and especially to Professor Hammoti for kindly invitation to this great conference. Thanks for your attention.
Thank you, Professor, for this very, very interesting conference, which gather all background about theoretical and computational vision of absorption of inhibitor on the metal surface field and other field also. Thank you for this this sharing. I am pleased to see on your presentation you have own Kaya equation.
Yes.
And Kaya descriptor. Very
Yes.
well. Congratulations. And now I am happy to listen to our colleagues to animate by their questions. Professor Nawi, I think that you have something to say.
Yes, first of all, I want to congratulate you because I have taught at the university quantum mechanics for many time, but through your conference, I learned very much today, and especially the hardness.
You are welcome, sir.
The hardness, which is the resistance toward electron cloud polarization.
Yes.
Which is the measure of the stability and reactivity of molecules.
Yes, 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 sir.
Yeah, and this is very important for our student to understand this, because if they understand this and they do some density functional theory, they can do a very good experiment to verify this kind of issues. I have just one question. Do you think that this hardness concept can be used for better in organic system or also in inorganic system?
Yes, sir. This hardness concept can be used for both inorganic system and organic systems. I am a theoretical inorganic chemist, For that reason, I am working especially on inorganic chemical spaces, but in the future studies, I will analyze using especially Kaya combined descriptor. I will analyze the organic reactions and organic reactions types.
Okay, I read your paper from 2015 on computational and theory chemistry. I think
Yes.
it's in is published in this journal, and this I learned a lot about it few time ago. Thank you very much.
Thanks, sir. Thanks a lot.
Yes, thank you, Professor Nawi. Is there any other question? Professor Tuzani, Professor Al-Ghazi.
Thank you, Professor Hamouti, for this nice conference. And thanks a lot for Professor Savak for this Kaya descriptor and Kaya DFT hardness. My question is, you test this equation for ligand with one metals, just ligand with one metals. If we have like a cluster, like with two metals or different oxidation, and can we use the same theory to dissolve these coordination systems?
Yes. Yes, Professor Rashid, thanks a lot for your questions. I can tell you, proposed hardness equation introduced in the light of hardness equalization principles of data can be used for all compounds, complexes, organic molecules, inorganic molecules. There is no any problem, and we can analyze neutral molecules and charged molecules using this equation. There is no any problem. Now, in Journal of Physical Chemistry A, we published a paper with Professor Laszlo von Szentpali that includes all answer for your questions. Thanks a lot.
Thank you, Professor Savak.
You are welcome.
Professor Hamouti, one question, please.
Go ahead, Professor Mhamdi, go ahead.
Okay, thank you, Professor Tuzani. Thanks you, Professor Sava, for this interesting presentation. En fait, my question is, it's possible to calculate the intensity of water and halogen bonds in aqueous solution, and to calculate the same bond, the intensity of the same bond at the interfaces of oxide and aqueous solution. It is possible to show the difference with in the intensity of this bond at the water interfaces with halogen ions, and at the interface, for example, for some oxides at our interface oxide solution. Thank you.
Yes. Professor Hassan, thanks for your questions. I can tell you we can use these equations for only gas phase. On the other hand, for solution phase, we cannot use. For solution phase, is it possible to use?
Thank you, Professor Savas.
You are welcome.
Is there any other question?
Just a short one, if there is no one.
Yes.
Yeah. Are you involved in machine learning, actually, to develop further your system and your research?
Sir, I am sorry, but I am not expertise on machine learning, but my collaborator Laszlo is working on this topic.
Okay. Very good. Okay, thank you.
You are welcome.
Professor Kaya, is there any difference between lattice energy
Yes.
and reticular energy?
I didn't understand, Professor Ammoti, what is particular energy?
Let's speak about lattice energy.
Lattice energy is the energy
Is
required.
it the same of reticular energy of a mineral compound?
Yes, using my lattice energy equation, we calculated and published the lattice energies of mineral compounds. There is no any problem, and there is an important way more in the literature. My collaborator, Professor Jenkins, proposed in equations to calculate. It's that equation is based on only molar volume. There is no chemical hardness in his equations. It is based on only molar volume, and you know that we can calculate molar volume of mineral materials in the light of their density and molar mass volumes easily. For that reason, I can tell you Jenkins methodology also is a useful tool for the calculation of the lattice energies of mineral compounds.
Yes. Professor Ebenso, have you
Welcome,
resolved
Professor Ebenso.
Professor Ebenso have a network very low and cannot interact with us. Have you solved this problem, Professor Ebenso? Waiting him. When we work on inhibition, yeah. Welcome, Professor Ebenso. You can speak.
Thank you very much. I think it's the network was here.
Thank you. You can interact with Professor Kaya. Waiting, Professor Ebenso. Professor Kaya, when
Yeah, I can.
Yeah.
Professor Moti, I well know Professor Ebenso. We are working together in some studies. I am very happy to work with him.
I'm so sorry, I can't join. I can't. My mic is low. Can you hear me?
Yes, of course. Great. Go on.
Okay. I'm saying I'm sorry. It's a network problem. That is why it took quite a long time to be able to listen. Thank you very much. Let me call my friend, Professor Amuti. My friend, we've been working for many years on corrosion inhibition in different systems. And I thought I could come for this very workshop, but unfortunately, because of the COVID virus, it's not easy to leave your country to another country. But I'm very glad and happy to be able to be here and to see all the people that I normally work with. I can see Rashid Tuzeni, Professor Amuti. I've also worked with Soyez too for some time. So I'm happy to be here. Thank you very much. We
are also happy to meet you, Professor Ebenso. and hope to meet you next ICMES 2021 in Morocco. And also to visit you in South Africa.
Yes, yes.
I return to
Looking forward to meeting you in South Africa in 2021.
Okay. Have you any question about the talk of Professor Kaya?
No, I don't have any question for him. Kaya
Okay.
is a very, I like his area of interest, theoretical modeling. I'm happy to listen to the last of his talk. I don't have any question.
Okay, thank you. Professor Kaya, when we change acid from hydrochloric acid to sulfuric acid or phosphoric acid,
Yes.
then the counter ions change.
Yes.
And then counter ions have acidity and
Yes.
basicity effects. Do you take into account the effect of counter ion of acids?
You said that, Professor, using my methodology, we can explain the acidity of molecules. True?
Yeah.
Yes. In the end of the presentation, I said that chemical reactions can be analyzed using Kaya combined descriptor for products and reactants. Calculating the Kaya combined descriptors, the acidity power of the acidity of the chemical compounds can be analyzed. Yes.
Okay. Is there any question about the in Facebook? There are so many congratulations and from our colleague. Is there any question, or we end this session to thank also Professor Kaya and his team in Turkey and in all around this beautiful world. And also I thank Professor Ebenso for his interaction with us, and hope that we may meet you again next time. May Allah give another chance. Okay.
Thanks a lot, sir. Professor Hamoti, next year we are waiting with Professor Goncagül, you, Professor Ebenso, Professor Rashid Tozani, Fadwa, my sister Fadwa El Hajjaji. We are waiting to Turkey, inshallah.
Inshallah, inshallah. Hope to meet you.
Yes. Thanks, sir.
Thanks for all, and good evening for all. And of course, ICMES 2020 will continue this conference tomorrow and until Saturday, the last conference. Thank you to your support and your presence, and goodbye.
Goodbye to all people.
Goodbye.
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 Bye. Assalamu alaikum. Allah.
C'est Hamouti, bonne soirée.
À vous aussi, chers collègues, et au plaisir donc de vous voir.
Okay. See you tomorrow.
Inch'Allah. Assalamu alaikum.
الحاج تبقى على خير.
الله يعطيكم الخير، تبارك الله عليكم. السلام عليكم.
يلا بسلام عليكم.
بروفيسور ساسي كومار، ويلكم.
ما سمعكش.
ايوا المهم اللي مهم في هذا الكونفرنس يعني الحمد لله on se connaît à travers the net and papers and الحمد لله هذه فرصة to meet colleagues
Yes.
on the work. تبارك الله عليكم.
رشيد وكاين البرد تماك ولا؟
راه السم ديال البرد اخويا عبد الرزاق.
كاين خويا واه راه il va pleuvoir دايرين غدا ان شاء الله.
ولا خلينا ندوز، ما خلينا ندوز، ما خليناش ندوز تماك.
رحنا غير نتيمو ما بقيناش كاع نتوضاو خايفين من البرد.
خلينا تدوز مع نحسوها هنا.
سي عبد الرزاق حبسها ليه، حبسها عنده.
تعرف البرد هنا عندنا في طوليدو 2 دوغري في الصباح، 1 دوغري 2 دوغري. من البارح اليوم كاين البرد. ما كاينش حتى في طوليدو، كاين السحاب، ولكن بلاص اخرين صبت فيهم الشتاء. ما عندناش الشتاء مازال ما وصلت.
حنا دايرين من اليوم ان شاء الله تبدل ان شاء الله.
لا ان شاء الله خاص الشتاء، لحقاش الجفاف دابا كاين كثير. كاين جفاف. والحاج وسولتي هذاك التكنيسيان سولتو
يوم الجمعة.
نعم.
لا هضر مع الحاج
هو الحاج راه معك.
سولتو التكنيسيان على ذاك الفيسبوك، وانا ما عرفتش غندير، والله ما عرفتش ندير. انا بغيت زعما يكونوا الطلبه يكونوا تصنتوا، ولكن انا خفت نديرها في الفيسبوك وسجلوها وهذه ما بغيتش تكون مسجله.
ان شاء الله. دابا هما راه حنا عندنا في الجامعه راه كاين اضراب وعندنا مشكله ديال الكونيكسيون. الحمد لله راه هذاك السيد جا وخدم معنا، شكرا جزيلا له.
مزيان. لا
كنا حصلنا غير مع كونيكسيون باش نديرو فوتو فيسبوك وهذه. ايوا راه غادي نهضر معاه دابا ان شاء الله ونجاوبك.
واخا انا سميتو عطيك واحد 3 العناوين ديال الناس اللي معايا بغاو تما يتصنتوا على سميتو هذا ديك المحاضره.
لا الا بغاو يتصنتوا المحاضره ولا صيفط الايميلات ديالهم للسي جفالي وصيفط لهم على الجوجل ميت ويبقاو معنا.
عطيني خليك ملي عندك الوقت اليوم، عندك واحد الوقت ارسل لي الايميل ديال جفالي يرسلوا لي.
جفالي هو إكماس 2020 السعيديه.
هو إكماس.
هو الماناجر التوب، هو البوس ديال
زعما خويا غير صافي كوبي.
إكماس 2020. واخا وشكرا.
ان شاء الله يوم مبارك، تبارك الله عليكم، شكرا جزيلا.